The night sky is a glittering illusion of peace. Behind every pinprick of light lies a reality of almost unimaginable ferocity. We are embarking on a countdown of the 30 most powerful stars in the known universe. This is not a simple list, but a journey to the cosmic extremes, where stars are not just balls of gas but titanic engines of creation and destruction. We will rank these celestial giants by the raw metrics of their power, their staggering luminosity that outshines entire galaxies of ordinary suns, their impossible mass that bends the laws of physics, their sheer physical size that dwarfs our entire solar system, and their explosive potential that can rewrite the night sky in an instant. By the end, you will understand the true scale of the universe's mightiest furnaces and the role they play in shaping everything, including the atoms that make you and me. We will meet a star so massive it is tearing itself apart with its own stellar winds, and another that is a ticking time bomb at the heart of our own galaxy. What does true cosmic power actually look like? Our journey begins with a cosmic champion, a star whose very existence challenges what we thought was possible. In the heart of a celestial spiderweb known as the Tarantula Nebula, within our neighboring galaxy, the Large Magellanic Cloud, burns a star named R13601. It is the most massive star we have ever found. To understand its scale, picture our own sun. Now, imagine taking 250 of them and crushing all that material into a single, ferocious point of light. That is the sheer mass of R13601, but mass is only part of the story of power. This star is an engine of such ferocious energy that it shines with the brightness of nearly 9 million suns. A single second of its output outshines what our sun will produce in an entire week. For decades, astronomers believed there was a firm ceiling on how big a star could grow, a limit of perhaps 150 solar masses before the radiation pressure from its own core would halt any further accumulation of material. R13601 shatters that idea, pushing the theoretical boundaries of stellar physics to their absolute brink. Yet this immense power comes at a terrible cost. The star is so luminous, so violently energetic, that it is engaged in a constant, desperate struggle against itself. It blows off a hurricane of its own substance in what we call stellar winds, streams of charged particles moving at millions of miles per hour. This star is not merely shining, it is evaporating, shedding the equivalent of Earth's entire mass every single month in a furious, self-destructive gale. It is a titan burning its candle at both ends, destined for a spectacularly short and violent life, a true heavyweight champion fighting a battle it cannot possibly win. That self-destructive fury of R13601 is not unique, merely taken to an extreme. Within our own Milky Way galaxy, we have a star that demonstrates what happens when such a titan truly begins to unravel. Meet Eta Carinae. For centuries, this star was a modest point of light in the southern constellation of Carinae. Then, in the 1840s, it did something astonishing. Over just a few years, it erupted with such violence that it became the second brightest star in the entire night sky, outshone only by Sirius. This event, known as the Great Eruption, was not a supernova. It was a monstrous stellar tantrum, a partial explosion where the star blasted off an enormous portion of its outer layers into space but somehow managed to survive. The result of that cataclysm is one of the most beautiful and eerie structures in the cosmos, visible only through powerful telescopes. We call it the Homunculus Nebula. It is a vast, twin-lobed cloud of gas and dust, shaped like an hourglass or a cosmic butterfly, expanding outward from the star at millions of miles per hour. Within those glowing lobes is enough material to make several of our suns, all violently ejected in that single historic event. Today, Eta Carinae remains one of the most unstable and closely watched stars in the sky. It is a hypergiant, a class of stars so rare and volatile that they are essentially ticking time bombs. Astronomers consider it the leading candidate for the next supernova to occur within our own galaxy. And its power is further amplified by a hidden secret. It is not one star, but two. Eta Carinae is locked in a deadly dance with a massive companion star, orbiting each other in a chaotic 5.5-year-long waltz. Their gravitational interactions and colliding stellar winds create an environment of unimaginable violence, likely priming the system for its final, catastrophic detonation. When it finally goes, it will be a spectacle unseen in our galaxy for centuries, a temporary new star that could shine as brightly as the full moon, a final, blinding testament to the power contained within such a fragile, unstable giant. But power in the cosmos is not measured by mass or luminosity alone. There is another dimension, one of staggering, almost incomprehensible physical scale. If you were to take the most massive star we just discussed and place it beside VY Canis Majoris, the contrast would be breathtaking. Where R13601 is a dense, furious powerhouse, VY Canis Majoris is a cosmic leviathan, a study in sheer, sprawling volume. This star is a red hypergiant, a class of stars so vast it represents one of the final, unstable chapters in the life of a true stellar giant. To grasp its size, let us perform a simple, mind-bending thought experiment. Our entire solar system, from the Sun out to the orbit of Jupiter, spans a distance of about 500 million miles. If you were to place VY Canis Majoris at the center where our Sun sits, its tenuous, glowing outer atmosphere would not just reach Jupiter, it would swallow it whole. The star's surface would extend out nearly to the orbit of Saturn, engulfing every planet from Mercury outward in a sea of roiling, crimson gas. This is not a star, it is a solar system in its own right. Yet, for all its immensity, VY Canis Majoris is surprisingly cool and faint per unit of its surface. It glows with a deep, ruddy light, a sign that its outer layers have expanded and cooled as the star nears the end of its life. It is shedding its own substance at a phenomenal rate, cloaking itself in a complex, beautiful nebula of its own ejected material. This surrounding cloud of gas and dust, lit from within by the dying giant's glow, tells the story of a star in its final, violent act of self-destruction. The fate of VY Canis Majoris is sealed. Within the next 100,000 years, a cosmic blink of an eye, its core will finally collapse. The resulting supernova will be a titanic event, outshining its entire host galaxy for a brief, spectacular moment. It will forge heavy elements and scatter them across space, and in its place, leave behind either a super-dense neutron star or a ravenous black hole. This colossal giant, a beacon of sheer physical presence, is a reminder that in the universe, even the largest and most enduring structures are merely temporary, destined to transform their immense power into the seeds of new creation. The title of the largest star is not a settled fact, but a prize constantly fought over in the shifting sands of astronomical data. For a time, that crown was held by a star named UY Scuti. Like VY Canis Majoris, it is a pulsating red hypergiant, a class of stars so immense and unstable that pinning down its exact dimensions is like trying to measure the exact edge of a cloud of smoke. The very outer layers of these stars are not solid surfaces, but vast, tenuous, and ever-changing atmospheres that fade gradually into the emptiness of space. So how do astronomers even begin to measure something so diffuse? They rely on a combination of precise techniques. First, they measure the star's angular diameter, its apparent size in our sky, using sophisticated instruments that can peer through its outer haze. Then they must know its distance from Earth with incredible accuracy. A tiny error in that distance calculation can mean the difference between a star being merely enormous and being record-breakingly colossal. This is where the debate between UY Scuti and VY Canis Majoris arises. Depending on the study and the methods used, the measurements shift. Some calculations place UY Scuti's radius at over 1,700 times that of our Sun. If it replaced our Sun, its photosphere, that fuzzy boundary we call its surface, would reach out between the orbits of Jupiter and Saturn. This makes its volume so incomprehensibly large that you could fit over 5 billion of our suns inside it. Yet other, more recent analyses suggest why Canis Majoris might be larger, or that another hypergiant like Stephenson 218 could hold the title. This uncertainty is not a failure of science, but a testament to the nature of these stellar behemoths. They are not static orbs, they are dynamic, pulsating entities, rhythmically expanding and contracting over years-long cycles while blowing off colossal winds of their own material. Their apparent size changes because they are literally changing. So the story of the largest star is a living one, a reminder that in the farthest reaches of our universe, we are often measuring not fixed points, but the breathing, dying size of cosmic giants. The debate over which star is largest unfolds in the distant, dusty arms of our galaxy, but one of the most powerful stellar giants is actually a familiar sight in our own night sky. Betelgeuse, the brilliant red star marking the shoulder of the constellation Orion, is a cosmic neighbor on the verge of a spectacular transformation. At roughly 700 light-years away, it is practically in our backyard by cosmic standards, close enough for our telescopes to capture astonishing details. This proximity makes it not just a beautiful point of light, but a vital laboratory for understanding the final, volatile years of a supergiant star. What we have learned is both mesmerizing and unsettling. The Hubble Space Telescope has revealed that Betelgeuse is not a uniform, smooth sphere. Its surface is a churning, bubbling cauldron of massive convective cells, each one larger than the entire orbit of Earth around the Sun. These are roiling plumes of superheated plasma rising from the star's unimaginably deep interior, making its surface look like a restless, uneven sea of fire. This dynamic activity directly causes the star's famous variability. Betelgeuse periodically dims and brightens as these colossal cells rise, cool, and sink back into the inferno, a visible sign of the titanic forces struggling within. In late 2019 and early 2020, the star dimmed dramatically, sparking worldwide speculation that its final collapse might be imminent. While that particular dimming event was likely caused by a vast cloud of ejected dust, the underlying truth remains: Betelgeuse is a ticking clock. It has exhausted the nuclear fuel in its core and is now fusing heavier elements in a desperate, unstable balancing act. Its fate is sealed. When that balance finally fails, the core will collapse in a fraction of a second, triggering a supernova explosion of staggering power. From our vantage point on Earth, the event will be a celestial spectacle unseen in human history. For several weeks, Betelgeuse will blaze in our daytime sky as bright as the full moon, a second sun visible even at noon. At night, it will cast faint, shimmering shadows. This is not a threat but a promise, a front-row seat to the death of a star and the birth of new elements that will one day be part of future worlds and perhaps future life. Its impending demise makes Betelgeuse one of the most important stars we study, a nearby preview of the ultimate fate awaiting all stellar giants. The violent finale of a star like Betelgeuse is not the only path to cosmic power. Some stars skip the slow expansion and choose a more direct, explosive route to self-destruction. This brings us to a truly exotic and ferocious class of stellar object, the Wolf-Rayet star. Imagine the core of a massive star, the blistering engine where nuclear fusion rages, suddenly exposed to the cold vacuum of space. That is essentially what a Wolf-Rayet star is. These are not whole stars in the traditional sense, but the stripped bare, naked cores of giants that have been violently peeled open. Their outer layers of hydrogen have been blasted away, either by their own incredible radiation or in a catastrophic interaction with a companion star. What remains is an intensely hot, helium-burning furnace, shining with a savage blue-white light and screaming its existence into the cosmos with winds of unimaginable ferocity. A perfect, terrifying example of this class is a star known as WR25, located within the same stellar nursery as Eta Carinae, the magnificent Carinae nebula. WR25 is a stellar powerhouse of almost pure violence. Its surface temperature soars to over 50,000 degrees Celsius, nearly 10 times hotter than our Sun. This heat translates into a luminosity over 6 million times greater than our own stars. But its true signature of power is not just its light, but its wind. The stellar wind streaming from WR25 is not a gentle breeze. It is a supersonic hurricane of charged particles, racing away from the star at speeds approaching 3,000 kilometers per second, millions of miles per hour. This wind is so potent, so dense with energy, that it is quite literally blowing the star apart. Each second, WR25 loses a mass equivalent to that of our entire moon. This is not a slow leak, it is a catastrophic, continuous eruption. The star is engaged in a furious act of stellar suicide, disassembling itself in real time and hurling its own substance across light years of space. In this ejected material are the heavy elements forged in its core, carbon, oxygen, and nitrogen, which are being seeded into the surrounding nebula. This violent process is a crucial recycling program on a galactic scale. The fury of a Wolf-Rayet star like WR25 enriches the cosmic environment with the very building blocks needed for new stars, planets, and ultimately, life. It is a stark reminder that creation in the universe is often preceded by an act of incredible, self-immolating destruction. The heart of our galaxy is a place of chaos and extreme violence. Here, in the crowded core of the Milky Way, we find a star that embodies that ferocity, a celestial monster known as the Pistol Star. It is a luminous blue variable, a class of star we have already met with Eta Carinae, but placed in an environment that amplifies its power to even greater heights. Imagine the core of a galaxy, a region packed with millions of stars, swirling gas, and the overwhelming gravitational pull of a supermassive black hole. In this cosmic pressure cooker, the Pistol Star burns with an almost inconceivable fury. Its true power is measured in raw, blinding light. Astronomers estimate that the Pistol Star shines with a luminosity 10 million times greater than that of our Sun. To put that in perspective, this single star emits as much energy in just 6 seconds as our Sun does over an entire year. Every moment of its existence is a cataclysmic release of power, a constant, searing flash that would vaporize any world foolish enough to orbit it. But such extreme brilliance does not go unnoticed by its surroundings. The star's power is not contained, it is actively sculpting the space around it. The Pistol Star is surrounded by a vast, beautiful cloud of gas and dust known fittingly as the Pistol Nebula. This nebula is not a remnant from the star's birth, but a creation of its ongoing violence. The star's intense ultraviolet radiation and its hurricane-force stellar winds, blowing at millions of miles per hour, are constantly slamming into the colder material of the galactic center. This relentless assault carves out cavities, shocks the gas into glowing, and shapes the nebula into its distinctive form, a clear and visible monument to the star's destructive influence. The Pistol Star is a lighthouse of pure energy in the galactic storm, a beacon that both illuminates and annihilates, demonstrating that in the densest regions of space, stellar power reaches its most concentrated and spectacular forms. The brilliant blue violence of Wolf-Rayet stars and luminous blue variables represents one extreme of stellar power, but there exists another kind of giant, one whose instability is cloaked in a deceptively familiar glow. Look toward the constellation Cassiopeia, that distinctive W shape in the northern sky, and you will find Rho Cassiopeiae. To the naked eye, it appears as a steady, yellowish point of light, but this is a profound illusion. Rho Cassiopeiae is a yellow hypergiant, one of the rarest and most unstable classes of star in the entire galaxy. Its placid color is a mask for a titanic, shuddering imbalance within. This star is so luminous that despite being over 8,000 light-years away, we can still see its gentle light without a telescope, a testament to its raw output, which is roughly 500,000 times greater than our Sun. Yet its true claim to fame is not its steady glow, but its spectacular failures. Rho Cassiopeiae is an eruptive variable prone to cataclysmic convulsions. In one recorded event, over a period of just a few months, the star violently ejected a shell of material with a mass equivalent to 10,000 Earths. This wasn't a gentle stellar wind, it was a sudden, colossal belch of the star's own atmosphere, flung into space at tremendous speeds. The eruption was so immense that it temporarily cooled the star's exposed outer layers, causing its spectral type, its cosmic fingerprint, to shift from yellow to a cooler red. It was as if the star changed its fundamental identity in a fit of cosmic rage. This behavior places Rho Cassiopeiae in a perilous and fascinating position on the Hertzsprung-Russell diagram, the map astronomers use to classify stars. It resides in what is known as the yellow evolutionary void. This is not a physical emptiness, but a theoretical zone of extreme instability. Stars in this region, with their particular combination of temperature and luminosity, cannot find a stable equilibrium. Their internal pressures and radiation forces are in a constant, violent struggle, making them prone to these massive eruptions and pulsations. They are stars in a desperate, frantic transition, caught between evolutionary states and tearing themselves apart in the process. Studying Rho Cassiopeiae is like watching a real-time experiment in stellar mortality, a rare chance to witness a fleeting and turbulent phase that few stars ever experience, a phase where power manifests not as steady brilliance but as catastrophic self-reinvention. The deceptive calm of a yellow hypergiant is one form of stellar instability, but there are other cosmic giants whose power is revealed through a slow, rhythmic dance of shadows. Far in the northern constellation Cepheus, a star named VV Cephei performs a spectacular celestial waltz. It is a red hypergiant, a class of star we now recognize as one of the largest and most volatile in existence, but with a crucial difference. VV Cephei is not alone. It is locked in a gravitational embrace with a much smaller, hotter blue companion star, together forming an eclipsing binary system. This partnership is not a peaceful one. It is a cosmic drama that unfolds over a staggering 20-year period. Every 2 decades from our vantage point on Earth, the smaller blue star disappears from view as it passes directly behind the colossal bulk of VV Cephei. This eclipse lasts for well over a year, a testament to the sheer physical scale of the primary star. But the true spectacle happens on the other side of the orbit. When the blue companion swings around and passes in front of the red hypergiant, it does not simply cross in front of a sharp edge. Instead, it plunges directly into the star's outermost atmosphere. For months, the hot blue star orbits within the tenuous, superheated outer layers of VV Cephei, a tiny spark navigating a sea of crimson gas. This intimate and violent interaction is a gift to astronomers. The precise timing of the eclipses allows for incredibly accurate measurements of the star's orbits, which in turn lets scientists calculate their masses and sizes with a confidence rarely possible for such distant, singular giants. We now know VV Cephei is a true behemoth with a radius over 1,600 times that of our Sun. If placed in our solar system, its surface would lie somewhere between the orbits of Jupiter and Saturn. Yet its mass is only about 25 times that of our Sun, a revealing detail. This star is a cosmic puffball, immense in volume but surprisingly lightweight for its size, meaning its outer layers are incredibly diffuse, almost like a luminous fog. This is precisely why its companion can orbit within them. As the blue star plows through this extended atmosphere, it creates immense shock waves, strips material away, and is itself bombarded by the hypergiant stellar wind. This ongoing theft of matter, a process called mass transfer, fuels intense activity around the smaller star and shrouds the entire system in complex clouds of gas and dust. VV Cephei's binary nature makes it a living laboratory, a place where we can directly observe the messy, gravitational interactions that shape the lives and deaths of the universe's most powerful stars. While the intricate dance of binary systems reveals stellar secrets, other giants announce their presence with a single, unforgettable color. Gaze toward the constellation Cepheus, and you may find a star that seems to burn with the deep, smoldering fire of a precious gem. This is Mu Cephei, famously known as the Garnet Star. Its rich, ruddy hue is not an illusion of our atmosphere, but its true nature shining across the void. In the late 18th century, the great astronomer William Herschel was so struck by its distinctive color that he described it as a very fine, deep garnet color, a name that has endured for over 2 centuries. That captivating garnet glow is a direct clue to the star's physical state. Mu Cephei is a red supergiant, a massive star that has swollen to a colossal size as it nears the end of its life. Its outer layers have expanded and cooled, radiating their energy as this deep crimson light, a sign of a surface temperature far cooler than our yellow sun, yet on a scale so vast it remains one of the brightest stars in its constellation. But its power is not expressed in steady brilliance. Mu Cephei is a semi-regular variable star, a prototype for an entire class of cool, pulsating giants. Its brightness is not constant. Over a complex cycle averaging around 860 days, it rhythmically swells and contracts, growing brighter and dimmer as it breathes in these slow cosmic breaths. This pulsation is the heartbeat of a dying star, driven by the unstable fusion of heavier elements in its core. While Mu Cephei may not hold the record for sheer size or luminosity, its historical and scientific significance is immense. For centuries, it has served as a vital bridge between naked eye observation and astrophysical theory. Its pronounced color and noticeable variability made it a recognizable subject long before we understood stellar evolution. It became a benchmark, a natural laboratory in the sky that helped astronomers categorize and comprehend the final, turbulent stages of massive stars. Watching the garnet star flicker is like watching a cosmic clock counting down. It is a beautiful, accessible reminder that the stars we see as fixed points are actually dynamic, living things, each telling the story of its own fiery evolution and inevitable transformation. A star's final act is not always a simple, explosive flash. Sometimes it is a slow, breathtaking revelation. In January 2002, a faint, anonymous star in the constellation Monoceros, the Unicorn, did something utterly perplexing. It flared to life with a sudden, violent brilliance, becoming over 600,000 times more luminous than our Sun. Astronomers initially thought it was a familiar story, perhaps a nova, a thermonuclear blast on the surface of a white dwarf. But V838 Monocerotis refused to follow the script. Instead of fading quickly, it lingered, and its behavior defied all expectations. The star did not expel its outer layers in a single, violent shell. Instead, it appeared to undergo a monstrous, rapid expansion. In a matter of weeks, its outer atmosphere ballooned outward at a staggering pace, swelling to a diameter larger than the orbit of Jupiter. As it expanded, its surface cooled dramatically, shifting from a blue-white inferno to a relatively cool red supergiant. This was not a star blowing up. It was a star inflating like a cosmic balloon, a process so bizarre it had no clear classification. The true wonder, however, was yet to come. Surrounding V838 Monocerotis was a vast, ancient cloud of dust, remnants from earlier, quieter phases of its life. When the star's brilliant flash of light erupted, it raced outward at the speed of light. But that light did not travel through empty space. As it reached successive shells of dust in the cloud, years and even decades later, it illuminated them from within. The Hubble Space Telescope captured this phenomenon in a series of iconic images, revealing what we call a light echo. It was not an explosion of material, but an explosion of illumination. The images show a breathtaking, ever-expanding halo of glowing dust, a cosmic ripple frozen in time, each ring marking where the light from that single, historic outburst had finally reached. This mesmerizing display was like watching a sonic boom made of pure light, a flashbulb going off in a dusty room and revealing its hidden architecture layer by layer. The cause of the eruption itself remains one of modern astronomy's great puzzles. The leading theory suggests a rare and catastrophic stellar merger where V838 Monocerotes swallowed a smaller companion star or giant planets in a single convulsive gulp. The energy from that digestion process then bloated the star to its incredible size. Whatever the trigger, this star stands as a powerful reminder that the universe holds phenomena we have not yet dreamed of, events where the most stunning spectacle is not the star itself, but the ghostly, illuminated echo of its past violence. The ghostly echoes of V838 Monocerotes reveal a universe of hidden violence, but some stars wear their instability on their sleeve. In the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, burns a star that gave its name to an entire class of cosmic catastrophes. S Doradus is the prototype luminous blue variable, the star that defines what it means to be brilliantly unstable. Its behavior is a masterclass in stellar extremes. For decades at a time, S Doradus can appear relatively calm, shining with the steady, searing light of a blue supergiant, but this calm is always an illusion. Periodically, the star undergoes a dramatic transformation. Over a period of years, it can erupt, swelling in size and brightening by a factor of 100 or more, becoming one of the most luminous objects in its entire galaxy. During these outbursts, its outer layers expand and cool, causing its color to shift from a fierce blue-white to a cooler yellow-white hue. It is as if the star is trying on a different identity, puffing itself up to an enormous size before eventually contracting back to its hot, compact state. This cycle of eruption and calm is not random. It is the visible signature of a star fighting a desperate internal battle. At its core, the furious radiation pressure from nuclear fusion is trying to blow the star apart, while the immense force of gravity is trying to crush it inward. In a star like S Doradus, these two titanic forces reach a precarious, temporary balance that periodically tips into chaos. The star becomes so luminous that its own light pushes against its outer layers, causing them to expand and cool in a great convective shudder. This process blows away massive amounts of material, creating a dense stellar wind that shrouds the star in its own ejected atmosphere. Studying S Doradus is like reading the instruction manual for stellar self-destruction. It provides the crucial link in the life cycle of the most massive stars. Astronomers now understand that luminous blue variables like S Doradus represent a critical transitional phase. They are massive stars in the process of violently shedding their hydrogen-rich outer envelopes. Each great eruption strips away another layer, peeling the star down to its hot, helium-burning core. This is the direct path to becoming an even more exotic and powerful object, a Wolf-Rayet star. S Doradus, in its furious pulsations, is literally transforming itself in real time, demonstrating how the universe's mightiest stars must tear themselves apart to be reborn in a new, even more ferocious form before their final cataclysmic supernova. The violent transformation of a star like S Doradus leaves behind more than just memories. It leaves physical monuments. Carinae is a masterpiece of such stellar sculpture. This brilliant blue hypergiant, another member of the unstable luminous blue variable class, is not merely a point of light. It is the radiant jewel at the center of one of the most perfect and beautiful nebulae ever discovered. Surrounding the star is a vast, nearly symmetrical ring of glowing gas and dust expanding outward into space. This is not a random cloud, it is a fossil record, a time capsule of the star's past fury. Every atom in that luminous ring was once part of Carinae itself, violently ejected in a series of titanic eruptions over the past 10,000 years. The nebula's stunning symmetry tells a story of a relatively calm, spherical ejection. Unlike the bipolar chaos seen around Carinae, it is as if the star blew a single, colossal bubble of its own substance, a bubble now lit from within by the star's ferocious ultraviolet radiation. This beautiful structure is a direct, visible measure of the star's power and its profound instability. Carinae is in a constant state of dramatic change, oscillating between two extreme personalities. For years at a time, it can exist as a searing hot blue hypergiant with a surface temperature soaring above 30,000 degrees Celsius. Then, it will undergo a great eruption, its outer layers expanding and cooling until it resembles a much cooler yellow hypergiant. During these cool phases, the star can lose an amount of mass equivalent to our entire Sun in just a few years, a rate of self-destruction that is almost unimaginable. This relentless shedding of material is the star's way of battling its own internal pressures, a desperate balancing act that cannot last. The beautiful ring nebula is the cumulative evidence of this struggle, the star's own history written in glowing gas. Carinae demonstrates with breathtaking clarity that the most powerful stars do not die quietly in the night. For tens of thousands of years before their final supernova, they are active artists, using their own substance as paint and their radiation as a chisel to sculpt the interstellar medium around them. They enrich the galaxy with heavy elements and create vast, intricate structures that will persist long after the star itself has vanished in a final flash. The ring of Carinae is both a tombstone for the star's lost mass and a cradle for future cosmic creation, a permanent signature of its temporary, glorious power. History itself can be written in starlight. In the summer of 1600, a new star blazed to life in the constellation Cygnus, the Swan. To astronomers of the time, it was a classical nova, a new star where none had been seen before. But this star, named P Cygni, refused to follow the rules. After its initial brilliant flare, it did not simply fade back into obscurity. It fluctuated, dimmed, then flared again, and ultimately settled as a permanent, prominent beacon in the night sky. It became a nova that never left, a historical anomaly that demanded an explanation for centuries. We now understand P Cygni not as a true nova, but as one of the Milky Way's rarest stellar beasts, a blue hypergiant. It is a star of such immense mass and luminosity that it spends its entire life on the verge of catastrophe, perpetually unstable. Its surface temperature is a blistering 19,000 degrees Celsius, and it shines with the light of over 600,000 suns. But P Cygni's greatest contribution to science is not its raw power, but the unique fingerprint it leaves on the light it emits. When astronomers first pointed their spectroscopes at this star, they saw something extraordinary. The spectral lines, which act like barcodes identifying chemical elements, appeared not as simple, sharp marks, but as broad, skewed profiles with a distinctive shape. Each line had a deep absorption component shifted slightly toward the blue end of the spectrum, and right beside it, a bright emission component. This bizarre pattern, now universally known as the P Cygni profile, is a direct snapshot of physics in action. It is caused by the star's own ferocious stellar wind. The absorption part is created as the wind, a vast shell of gas blowing directly toward us, blocks some of the star's light at a specific wavelength. The emission part comes from that same shell of gas, glowing brightly as it expands outward in all directions. This single, persistent star gave astronomers a universal diagnostic tool. Today, whenever we see a P Cygni profile in the spectrum of any star, quasar, or even an entire galaxy, we know we are looking at a powerful, directed outflow of material. It is a signature of mass loss on a cosmic scale. So P Cygni stands as a profound link between eras. A star whose unexpected behavior in the 17th century now provides the key to measuring the violent winds that shape the evolution of the most powerful objects across the universe. That signature of a stellar wind, the P Cygni profile, is etched into the light of stars across the cosmos, but one of its most potent examples is actually a familiar sight for southern sky watchers. Zeta Puppis, also known by its ancient name Naus, is a beacon of pure, raw stellar fury. It is the brightest O-type star in the entire night sky, a classification reserved for the hottest, most massive, and shortest-lived stars in existence. If you were to stand on a hypothetical planet near Naus, you would not see a gentle yellow sun, but a searing, actinic blue point of light so intense it would cast sharp, black shadows. Its surface simmers at a staggering 40,000 degrees Celsius, over 7 times hotter than our Sun. This incredible heat translates into a luminosity over 20,000 times greater, a ceaseless torrent of energy that makes it one of the most powerful engines in our galactic neighborhood. But Naus holds another, more dynamic secret. This star is not merely powerful, it is a fugitive. Astronomers classify it as a runaway star, a celestial cannonball hurtling through space at breakneck speed. It is moving through the galaxy at over 60 kilometers per second, a velocity so great it has already traveled a considerable distance from the stellar nursery where it was born. The most compelling theory for this incredible speed is a story of cosmic betrayal and violent birth. Naus likely began its life in a tight binary system, bound by gravity to an even more massive companion. That companion, living fast and dying young, eventually exhausted its fuel and collapsed in a supernova explosion. The sudden, asymmetric detonation would have acted like a cosmic slingshot, violently ejecting the surviving star, which we now know as Naus, and sending it careening across the galaxy like a stone from a shattered window. This tumultuous past is written in its present. As a lone O-star, Naus now plows through the interstellar medium like a ship through water, its powerful stellar wind, 1,000,000 times stronger than the solar wind, carving a vast bow shock ahead of it. This wind is so dense and fast that it strips the star of a mass equal to our Sun every 100,000 years, a phenomenal rate of loss. For astronomers, Naus is a gift. Its relative proximity and naked eye visibility make it a perfect nearby laboratory. By studying the intricate details of its spectrum, including those telltale P Cygni profiles, scientists can decode the physics of its churning atmosphere, measure the precise composition and speed of its wind, and understand the mechanisms that drive such phenomenal mass loss in the universe's hottest stars. It is a runaway engine of creation, a solitary traveler whose brilliant light and violent history illuminate the chaotic processes that govern the lives of the galaxy's most elite stellar class. Naus is a cosmic cannonball, but it is far from the fastest. Alpha Camelopardalis, a star hidden in the faint northern constellation of the Giraffe, redefines the very meaning of a runaway star. This is not a star merely drifting from its birthplace. It is a stellar projectile fired from a galactic gun. Alpha Cam is racing through the interstellar void at a velocity that defies belief, over 1,000 kilometers every single second. At that speed, you could travel from the Earth to the Moon in under 7 minutes. This incredible motion is a permanent scar from a violent past, likely born in one of 2 ways. Perhaps it was once part of a tight binary system where its companion star exploded as a supernova, the asymmetric detonation violently ejecting it like a stone from a sling. Or it may have suffered a close gravitational encounter with other massive stars in its dense natal cluster, a celestial game of billiards where it was flung out into the galactic wilderness. Whatever the precise trigger, the result is a star on a solitary, high-speed journey with profound visible consequences. As Alpha Cam hurtles through space, it does not travel through a perfect vacuum. It plows into the thin gas and dust of the interstellar medium. the star's own powerful stellar wind, a supersonic stream of charged particles, slams into this material ahead of it. This collision creates a titanic shock wave, compressing and heating the gas to immense temperatures. To our eyes, this structure is invisible, but to infrared telescopes, it glows brilliantly. We see a vast, arcing wall of energized material called a bow shock, shaped exactly like the wave that forms at the prow of a speeding ship. This luminous arc stretches for light years ahead of the star, a permanent testament to its incredible speed and power. Alpha Camelopardalis is more than just a stellar curiosity. It is a dynamic illustration of the violent ecology within star clusters. Its existence proves that these stellar nurseries are not gentle places, but chaotic arenas where gravitational encounters and stellar deaths can literally catapult entire suns across the galaxy. This star's lonely, high-velocity journey shows us that the cosmos is in constant, often violent motion, where even the mightiest stars can become projectiles in a celestial shooting gallery. Deep in the same chaotic heart of the Milky Way that forged the Pistol Star, another titan burns with a nearly equal ferocity. WR102 Ca, known to astronomers as the Peony Star, is a Wolf-Rayet monster that stands as a direct rival to its more famous neighbor. This star is a beacon of pure, unadulterated power, ranking among the most luminous stars ever discovered within our own galaxy. Its brilliance is staggering, estimated to be over 3 million times that of our Sun, a searing output that places it firmly in the same elite league as the Pistol Star itself. The Peony Star's light, however, tells a specific and violent story. When analyzed through a spectroscope, its light reveals the classic, frenzied signature of a Wolf-Rayet star, dominated by broad, powerful emission lines of helium, carbon, and oxygen. These are not the calm absorption lines of a normal star's atmosphere, but the screaming announcements of a star in the process of violently disassembling itself. They are generated in the colossal, expanding shell of its own ejected material, a shroud of superheated gas being blasted outward by the star's phenomenal radiation pressure. This stellar wind is so dense and fast that it strips the star of a sun's worth of mass every few thousand years, a rate of self-cannibalization that is almost beyond comprehension. Yet for all its raw power, the Peony Star would remain hidden to our eyes. It resides in a region of the galactic center thick with interstellar dust, a cosmic murk that absorbs and scatters visible light. To peer through this veil, astronomers must turn to the eyes of infrared telescopes. At these longer wavelengths, the obscuring dust becomes transparent, revealing the star's true, fiery glory. What we see is a point of intense infrared radiation, a hidden sun blazing in the dark. WR102 Ca represents a critical, fleeting peak in the stellar life cycle. It is a star that has already shed its outer hydrogen layers, exposing its naked, helium-fusing core to the vacuum of space. This phase is the ultimate expression of stellar energy output before the final, inevitable collapse. The star is burning its remaining nuclear fuel at a frantic, unsustainable pace, racing toward its destiny as a supernova. In the dusty core of our galaxy, the Peony Star shines as a brilliant and short-lived testament to the violent zenith a star can reach, a final, furious flash of light before the darkness of a black hole or the scattered seeds of a supernova remnant take its place. The galactic center is not the only place where stellar titans forge their legacy. In the dazzling tapestry of the Carinae Nebula, a cosmic masterpiece of glowing gas and dark dust, one star reigns supreme. HD 93129 is the brilliant heart of this stellar nursery, an O-type supergiant of almost unimaginable ferocity. It is not a solitary ruler, but one half of a colossal binary system, bound by gravity to another massive star in a tight, fast orbit. Together, they form a powerhouse of radiation and stellar wind that dominates their corner of the galaxy. But the true measure of HD 93129A's power is not just its own blinding light, which outshines our Sun by over 5 million times, but its profound influence on its surroundings. This star acts as a cosmic lighthouse, bathing the Carinae Nebula in an unrelenting torrent of ultraviolet radiation. This high-energy light does not simply illuminate the nebula, it fundamentally transforms it. When a UV photon from the star strikes a neutral hydrogen atom in the surrounding cloud, it violently strips away the atom's electron, a process we call ionization. This act of cosmic violence is the very engine that paints the nebula's famous glow. The freed electrons, careening through space, eventually recombine with protons, releasing energy in the form of the beautiful, characteristic red light of hydrogen alpha emission that gives the nebula its ethereal color. But the star's influence goes far beyond mere illumination. The intense pressure from its radiation and its powerful stellar wind physically compresses the surrounding gas and dust, carving out vast cavities and sculpting the iconic pillars and mountains seen in Hubble's famous images. This compression is a trigger. It can push cold, dense clouds of material over a critical threshold, causing them to collapse under their own gravity and ignite new stars. In this way, HD 93129 is a paradoxical force of both destruction and creation. It is eroding the nebula from which it was born, while simultaneously providing the shock and pressure needed to spark the next generation of suns. This single star, a dominant force in a spectacular binary, exemplifies the central role of the universe's most powerful stars. They are not passive points of light, but active architects, using their raw energy to shape the structure and future of entire galactic ecosystems. Our own galaxy provides a stunning gallery of stellar extremes, but to truly understand the laws that govern these titans, we must look beyond the Milky Way. A mere 3 million light-years away, in the graceful spiral arms of the Triangulum galaxy known as Messier 33, burns a star named VAR 83. It is a beacon of such intense power that it stands as one of the most luminous objects in its entire host galaxy, a clear signpost of a familiar yet alien phenomenon, a luminous blue variable. Observing VAR 83 is like looking into a cosmic mirror, but one that reflects a slightly different reality. Here, in a separate island universe with its own unique history of star formation and chemical composition, we find a star behaving almost identically to its cousins like S Doradus and Eta Carinae back home. It undergoes the same dramatic eruptions, swelling in size and brightness, shedding its outer layers in great convulsive gusts. This profound similarity is not a coincidence, it is a confirmation. It tells us that the fundamental physics of stellar interiors, the titanic battle between radiation pressure and gravity, operates under the same universal rules, no matter where in the cosmos you look. The existence of VAR 83 proves that the blueprint for building and destroying a hypergiant is written into the fabric of reality itself. Yet, studying these stars in other galaxies offers more than just confirmation. It provides a priceless, broader sample. Luminous blue variables are extraordinarily rare and short-lived, making them like cosmic mayflies. In our own Milky Way, we can count the known examples on two hands. By looking at galaxies like Messier 33, we can find more of these elusive giants, observing them at different ages with different chemical makeups and in different galactic environments. Each one is a critical data point. They help us answer urgent questions about their role in galactic evolution. How much material do they actually eject into space? What is the precise mix of heavy elements like carbon, oxygen, and nitrogen that they forge in their cores and then scatter with their winds? These are not abstract queries. The violent outflows from stars like VAR 83 are the primary delivery system for enriching a galaxy's interstellar medium with the raw ingredients for rocky planets, organic molecules, and ultimately, life. By cataloging the power and output of luminous blue variables across the local universe, we are essentially taking inventory of a galaxy's future potential. VAR 83, shining brilliantly in a neighboring spiral, is a remote but crucial laboratory, demonstrating that the most self-destructive acts of stellar power are paradoxically a universal and essential force for creation. The story of stellar power is often a family affair, within the same dense, violent heart of the Tarantula Nebula that gave us the champion R13601. Its close siblings are rewriting the rules of star formation. R136A2 and A3 may not hold the absolute record, but they are far from ordinary. Each of these stars is a colossal engine in its own right, weighing in at well over 150 times the mass of our Sun. To find one such titan is extraordinary, but to find three of them, along with several other giants, all packed into a region of space just a few light years across, is a cosmic anomaly that forces us to rethink our textbooks. This dense cluster, known as R136, is a stellar factory operating at maximum output. Its existence suggests that under the perfect conditions, an environment of incredibly dense, cold gas, flooded with the right mix of elements, and perhaps triggered by the shockwaves from earlier supernova nature, can build stars on a scale we once deemed impossible. The traditional model suggested a firm upper limit, a ceiling where a star's own fierce radiation would blow away the gas cloud feeding it, preventing further growth. But R136 laughs at that limit. Here, in this cosmic pressure cooker, the gas was so dense and the gravitational pull so overwhelming that multiple protostars could gorge themselves, accreting material at a breakneck pace and growing to these monstrous proportions before their own stellar winds could switch on and halt the feast. This cluster is not just a collection of record breakers, it is a living laboratory showing us that the upper bounds of stellar mass are not set by a single, universal law, but by the specific, chaotic environment of a star's birth. The presence of these sibling titans burning side by side tells us that when the universe decides to build giants, it often builds them in batches. The dense, violent clusters of the Tarantula Nebula seem to be the only nurseries capable of birthing stellar titans, but the universe loves a good mystery. Drifting in the sparse outskirts of that same large Magellanic Cloud, far from the brilliant chaos of 30 Doradus, a solitary beacon burns with a fierce, lonely light. This is VFTS 682, a star that should not exist where it is. It is a massive, searing hot star, shining with the luminosity of over 3 million suns and classified as a Wolf-Rayet star, a type we know is the exposed, dying core of a giant. Yet here it sits in splendid isolation, with no major star-forming region or dense cluster in sight. Its very location is a profound puzzle. How did a star of such immense power, a star that requires a vast reservoir of cold gas to form, end up so utterly alone? Astronomers face two compelling, yet equally dramatic possibilities. The first is a story of cosmic ejection. Perhaps VFTS 682 was born in the frenzied core of the Tarantula Nebula itself, a sibling to R136. In that gravitational maelstrom, a close encounter with other massive stars or the asymmetric kick from a companion supernova could have violently flung it outward like a stone from a slingshot, sending it on a high-velocity journey to its current lonely vantage point. We have seen this with runaway stars like Alpha Camelopardalis. The second possibility is even more radical. Could VFTS 682 have formed right where we see it, in isolation? This idea challenges a fundamental pillar of star formation theory, that the most massive stars require the immense pressure and dense fuel of a giant molecular cloud's heart to collapse and ignite. If this star truly formed in solitude, it forces us to reconsider if there are unknown, quieter pathways to building giants, perhaps through the slow, steady accumulation of material in a small, dark cloud that somehow avoided fragmenting into many smaller stars. VFTS 682, a brilliant question mark against the dark, compels us to admit that for all we know about stellar power, we are still learning the rules of where and how that power is born. The Tarantula Nebula is a cosmic forge that seems to specialize in producing stellar giants. Among the brilliant chaos of its central cluster, R136, another Titan commands attention, a star known as Melnick 42. This is not a fading red hypergiant, but a star in the prime of its life, a searing blue O-type supergiant burning with ferocious intensity. Its surface temperature soars to over 47,000 degrees Celsius, making it one of the hottest stars known in the entire Large Magellanic Cloud. This incredible heat translates directly into raw, blinding power. Melnick 42 shines with a luminosity estimated at over 1 million times that of our Sun, a ceaseless torrent of energy that floods its surroundings. In terms of sheer mass, it is a heavyweight contender, weighing in at around 190 solar masses. This places it firmly among the most massive stars ever catalogued, a true sibling to the R136 cluster just a few light-years away. The existence of Melnick 42, R136, and dozens of other supergiants packed into this one nebula is not a random accident. It defines a special class of cosmic environment known as a starburst region. This is a place where the conditions for star formation have reached a fever pitch, where vast reservoirs of cold gas collapse under gravity at a rate hundreds or even thousands of times faster than in a typical galactic neighborhood like our own. The result is a spectacular, concentrated burst of stellar birth, producing a dazzling fireworks display of the most massive and powerful stars the universe can build. For astronomers, this density of stellar power is a priceless gift. It is like finding a natural laboratory where all the most extreme experiments in stellar physics are running simultaneously, side by side. By studying a whole population of these titans in one place, scientists can do something remarkable. They can calibrate the fundamental laws that govern them. They can precisely measure how a star's mass relates to its luminosity, its temperature, and the ferocity of its stellar winds. They can observe how these factors together dictate a star's ultimate lifespan, watching as the most massive members race through their nuclear fuel in just a few million years, a mere blink compared to our Sun's 10 billion-year journey. This crowded stellar metropolis allows for direct comparisons, helping to refine our models of stellar evolution and answer critical questions. How does the intense radiation from one hypergiant influence the formation or stability of its neighbors? What is the total collective impact of their winds and eventual supernova on the structure of the nebula itself? Each brilliant point of light, like Melnick 42, is a data point in a grand cosmic equation, helping us decode the life cycle of power itself. From the violent ignition of a star to the seeds of destruction it will one day scatter across the galaxy. This family of titans, born in crowded nurseries, often faces a violent and solitary future. BD plus 43 degrees 3654 is a stellar fugitive on an epic journey. This brilliant O-type supergiant is not merely drifting, it is hurtling through the Orion spur of our galaxy at a breathtaking speed of over 160 kilometers per second. Its motion is so extreme that it has traveled a vast distance from the Cygnus OB2 association, the dense stellar cluster believed to be its birthplace, a cosmic home it can never return to. The star's incredible velocity is permanently etched across the heavens, not in its visible light, but in the dramatic structure it creates in its wake. As BD plus 43 degrees 3654 plows through the thin gas of the interstellar medium, its powerful stellar wind, 1,000,000 times stronger than our Sun's solar wind, smashes directly into this material. The collision is titanic. It compresses and superheats the gas, forming a vast, arcing wall of energized particles that glows brilliantly in infrared light. To our telescopes, this structure appears as a perfect crescent-shaped bow shock, a cosmic wave frozen ahead of the speeding star, much like the bow wave that builds before a speedboat cutting through water. This luminous arc is a direct and beautiful testament to the star's raw power and motion, a visible signature of its interaction with the galaxy itself. The question of its origin is a tale of stellar youth turned violent. How does a star achieve such a tremendous speed? Astronomers see two likely dramatic pathways. The first is a story of gravitational chaos. In its dense natal cluster, BD plus 43 degrees 3654 may have suffered a close encounter with other massive stars. In this celestial game of billiards, complex gravitational interactions could have slung it out of the cluster at high velocity, a runaway ejected by the very society that birthed it. The second possibility involves a more intimate betrayal. The star may have once been part of a tight binary system. If its more massive companion star exhausted its fuel and exploded as a supernova, the sudden, asymmetric detonation could have acted like a cosmic cannon, violently ejecting the surviving star and propelling it on its lonely, high-speed trajectory. Both scenarios highlight a fundamental truth about the lives of the most massive stars. Their beginnings are often as chaotic and explosive as their ends. BD plus 43 degrees 3654, with its brilliant bow shock carving a path through the void, is a permanent monument to that chaotic youth, a solitary engine of light on a one-way trip across the galaxy. This lonely, high-speed journey is a prelude to a star's ultimate transformation. In the constellation Aquila, a star named IRC plus 10420 is performing a cosmic magic trick in reverse. It is not expanding and cooling like a typical aging giant, but is instead caught in the act of violently contracting and heating up. This star is a yellow hypergiant, but its behavior is anything but stable. It is shrouded in a vast, complex envelope of its own expelled material, a dusty cocoon of gas and silicate grains that glows brilliantly in the infrared, hiding the true star within. What makes IRC plus 10420 so extraordinary is the story this envelope tells. The star is not calmly shedding its outer layers, it is violently ejecting them in a series of colossal eruptions, losing mass at a rate millions of times greater than our sun's solar wind. Each eruption adds another shell to the intricate, onion-like structure surrounding it, a fossil record of its recent turbulent past. But the most startling clue lies not in the ejected material, but in the star itself. Over the past few decades, astronomers have witnessed its surface temperature rising dramatically. This is the opposite of what we expect from a dying star. Typically, a massive star swells into a cool, red supergiant before its final collapse. IRC plus 10420 seems to be rewinding that process. The prevailing theory is that we are catching it in a brief, frantic transition. It may have already been a red supergiant, but a series of powerful eruptions has stripped away so much of its bloated, cool outer atmosphere that the hotter, denser interior layers are now being exposed. The star is essentially peeling itself, moving backward on the temperature scale from red to yellow, and it may not stop there. It appears to be on a direct path to becoming a Wolf-Rayet star, a naked, helium-burning furnace screaming its existence into the void. This makes IRC plus 10420 a rare and precious time capsule. We are witnessing a short-lived evolutionary phase that most massive stars undergo in mere thousands of years, a cosmic blink of an eye. It is a star caught in the act of metamorphosis, violently dismantling one identity to assume another, more ferocious form, providing us with a real-time tutorial on how the universe's mightiest engines prepare for their final, spectacular performance. That violent metamorphosis is a prelude to a final, definitive flash. In the southern constellation of Carinae, a star named Schur 25 is quietly assembling the props for its own cosmic finale. This is not a hypergiant or a luminous blue variable, but a blue supergiant, a star that has already passed through its red giant phase and contracted back into a hot, compact, and highly unstable form. What makes SHIR 25 so captivating is not just the star itself, but the beautiful and ominous structure that surrounds it. Encircling the star is a near-perfect hourglass-shaped nebula, a ring of glowing gas and dust that looks eerily, almost exactly, like the famous ring that surrounded supernova 1987A, the closest observed supernova in modern history. That supernova, which exploded in the Large Magellanic Cloud in 1987, was preceded for thousands of years by a ring of material ejected by the doomed star. SHIR 25 appears to be in the exact same preparatory stage. It is a supernova imposter, a star that is not yet exploding but is clearly broadcasting the violent activity that precedes the final cataclysm. The perfect symmetry of its ring tells a story of a relatively calm, spherical ejection of material, likely occurring when the star was in a previous, cooler phase. Now, as a blue supergiant, it is burning the last of its nuclear fuel at a frantic pace. Astronomers consider SHIR 25 a prime candidate for the next core collapse supernova to occur within our Milky Way galaxy. Its location, its spectral type, and most importantly, the presence of that telltale ring all point to a star that has entered the final chapter of its life, measured not in millions of years, but perhaps in mere thousands or even centuries. For scientists, SHIR 25 is a precious warning sign, a cosmic alarm clock ticking down to an event of unimaginable power. It offers a rare chance to study the pre-supernova environment in detail, to understand what a star does in the centuries just before it dies. When SHIR 25 finally does collapse, its ring will be lit up from within by the flash of the explosion, creating a spectacular echo of light that will teach us more about the final moments of stellar life than any telescope observation could before. It is a dormant firework, its fuse already lit, waiting for the moment when the flame reaches the core. The clock is ticking for every stellar giant, but some are surrounded by the ghosts of their peers. Westerlund 1-26 is a crimson leviathan that burns within a stellar graveyard of astonishing pedigree. This red supergiant, or perhaps even a hypergiant, is not drifting alone in the galactic void. It is the most prominent resident of Westerlund 1, a cluster of stars so dense and massive it is considered a young globular cluster, a rare and extreme family of stars born in a single, furious burst of creation. To stand within this cluster would be to witness a sky filled with brilliant, short-lived giants, a dazzling but deadly neighborhood. Westerlund 1-26 itself is a study in sheer physical scale, with a radius estimated to be over 1,500 times that of our Sun. If placed at the center of our solar system, its tenuous outer atmosphere would swallow the orbit of Jupiter and reach nearly to Saturn. Yet its true significance lies not just in its own immensity, but in the company it keeps. This cluster is not a nursery of infant stars, but a collection of stellar adults, many of which have already met spectacular ends. Scattered among the surviving giants are the bizarre, ultra-dense remnants of their siblings, including multiple magnetas. A magneta is a type of neutron star with a magnetic field so powerful it could strip the data from every credit card on Earth from halfway across the galaxy. These objects are the corpses of massive stars that have already exploded as supernova. Their presence in Westerlund 1 is a silent, powerful testimony. It tells us this cluster once contained not just a few large stars, but an entire population of the most massive and powerful stellar engines the galaxy can produce, stars that lived fast, died young, and left these incredibly exotic graves behind. Westerlund 1-26, therefore, is more than a solitary giant. It is a surviving elder in a community of extremes, a living reminder that the universe's greatest concentrations of stellar power are often found in these dense, violent clusters. Here, stars are born together, shine with ferocious collective brilliance, and die in rapid succession, their death seeding the environment with the elements and the exotic physics that will shape the next cycle of cosmic evolution. The dense, violent clusters that forge stellar giants also become their graveyards. The death of a star like those in Westerlund 1 does not mark an end to its power, only a transformation into something even more bizarre and concentrated. The story of CXOJ 164,710 to 455,216 begins with a cataclysm we can no longer see. It was once a member of that very cluster, a massive star that lived fast, burned bright, and ultimately exhausted its fuel. Its core collapsed under its own weight in a fraction of a second, triggering a supernova that outshone its entire galaxy, but the star did not vanish. In that unimaginable collapse, its core was compressed into a sphere of pure nuclear matter just a dozen miles across, a neutron star. This particular remnant, however, is no ordinary neutron star. It is a magnetar, and it represents one of the most terrifyingly powerful objects in the entire cosmos. A magnetar is a neutron star born with a unique and monstrous advantage, an off-the-charts rotation speed, and a perfectly aligned dynamo-like interior. As the star's core collapsed, its already intense magnetic field was squeezed and wound tighter, amplified to levels that defy human intuition. The magnetic field around CXOJ 164,710 to 455,216 is so strong it reaches approximately 1 quadrillion times the strength of Earth's magnetic field. To grasp that scale, consider this: if a magnetar were located halfway between the Earth and the Moon, its magnetic field would be strong enough to strip the information from every credit card on our planet. It would magnetize the atoms in your body, pulling on the water molecules within you from 250,000 miles away. This is not a gentle force, it is a fundamental distortion of space itself. This unimaginable magnetic power does not lie dormant. The crust of a magnetar is a solid lattice of iron, but under the strain of that titanic magnetic field, it undergoes colossal starquakes. Think of the tectonic plates on Earth shifting to cause an earthquake, but here, the entire crust of a star, a shell a mile thick and harder than diamond, suddenly cracks and shifts. These are not mere tremors. A single starquake on a magnetar releases more energy than our sun will emit over 100,000 years. That energy is unleashed in a flash of gamma rays, the most energetic form of light in the universe. In 2006, a magnetar in another part of the galaxy released a flare so powerful that, despite being 50,000 light-years away, it compressed Earth's upper atmosphere and briefly blinded orbiting satellites. For a tenth of a second, it was brighter than the full moon, outshining every other source of gamma rays in the observable universe. CXOJ 164,710 to 455,216 is capable of the same violence, a dormant dragon in the heart of Westerlund 1. This object, invisible to our eyes, completes a crucial cycle in the story of stellar power. It is the direct, hyper-compressed descendant of the most massive stars. The furious rotation and dense core needed to create a magnetar come from a progenitor star that was itself a titan, spinning rapidly and living a short, explosive life. The magnetar is the ultimate concentration of that star's legacy, taking the raw power of its gravity and magnetism and focusing it into a realm of pure, destructive physics. It shows us that the death of a star is not an extinguishing of power, but a metamorphosis into a new, even more extreme form, where the rules of our universe are stretched to their absolute breaking point. That terrifying magnetic legacy is a product of chaotic collapse, but the universe has another, more precise method for stellar annihilation. Pegasi is a cosmic diamond with a fatal flaw. This star, located just 150 light-years away, is not a giant. It is a white dwarf, the Earth-sized, super-dense remnant of a sun-like star that has already died. Its power lies not in its current state, but in its future and in the deadly partnership it maintains. Ik Pegasi is locked in a tight 21-day orbit with a normal main sequence companion star similar to our own Sun. This proximity is the key to its coming cataclysm. The white dwarf's immense gravity is actively stealing hydrogen-rich material from the outer layers of its living companion. This stolen gas does not simply fall onto the white dwarf's surface. It spirals down, forming a hot, luminous disk of accreting matter before finally settling onto the star itself. Here, in the heart of this dead cinder, a slow-motion bomb is being assembled. The white dwarf is composed primarily of carbon and oxygen, packed together under degenerate electron pressure, a quantum mechanical force that prevents further collapse. As more and more hydrogen from its companion piles onto the surface, it is compressed and heated by the dwarf's intense gravity. Eventually, the bottom layer of this hydrogen blanket undergoes runaway nuclear fusion, igniting in a violent but surface-level explosion we call a nova. This can happen repeatedly, but Ik Pegasi has a far more final destiny. It is very close to a critical threshold known as the Chandrasekhar limit, a mass of about 1.4 times that of our Sun. If the steady accretion of material pushes it over that limit, the quantum pressure that supports it will catastrophically fail. In a fraction of a second, the entire white dwarf will not just ignite on its surface, but will undergo a total thermonuclear detonation from the inside out. There will be no core left behind, no neutron star or black hole. The entire star, every atom of it, will be vaporized in what we call a Type Ia supernova. The power of this event is so standardized and so immense that it becomes a cosmic lighthouse. For a few weeks, this single exploding white dwarf will shine with a peak luminosity 5 billion times that of our Sun, briefly outshining every other star in its entire host galaxy combined. This is a different kind of stellar power altogether. It is not the raw, lifelong fury of a massive hypergiant, but the precise, stored potential of a dead star reignited by a binary partner. Ik Pegasi is the nearest known candidate for such an event to Earth. Its inevitable explosion, which could happen in 1 million years or far sooner, will be a spectacle that rewrites its corner of the Milky Way, dispersing iron, nickel, and other heavy elements forged in its total annihilation across space, seeding future generations of stars and planets with the very elements that make worlds like ours possible. The silent, ticking bomb of Ik Pegasi represents one fate for a binary system, but the universe has a far more spectacular and immediate display of stolen power. Deep within the constellation Aquila, a system named SS433 performs a continuous high-energy ballet that redefines the very concept of a star. At first glance, it appears as an unremarkable point of light, but this is a profound illusion. SS433 is not a star at all. It is a microquasar, a scaled-down version of the monstrous quasars that blaze at the hearts of distant galaxies. Here in our own Milky Way, this system demonstrates the same terrifying physics on a local stage. The engine is a compact object, either a black hole or a neutron star, locked in a tight orbit with a massive, bloated companion star. The compact object's immense gravity is a relentless thief, constantly stripping material from its partner. This stolen gas does not fall directly in, but spirals into a superheated, whirling disk of plasma called an accretion disk, a cosmic whirlpool of matter screaming in X-rays as it is dragged toward the point of no return. But SS433's true signature of power is not this inward spiral, but what it shoots outward. From the poles of this accretion system erupt two narrow, opposing beams of matter, moving at a staggering 26% of the speed of light. These are relativistic jets, and they are tipped with what astronomers call atomic bullets, dense clumps of iron and other heavy elements hurled into the void. These jets are not steady streams. They perform a slow, majestic wobble or precession, like a spinning top winding down, completing a full cycle every 162 days. This procession carves out a vast, corkscrew-shaped path in the surrounding nebula, a permanent helix of energy etched across light-years of space. The raw power channeled into these focused beams is mind-boggling, dwarfing the total energy output of the companion star's nuclear fusion. All that energy originates not from burning fuel, but from the incredible gravitational potential of matter screaming down into the deep well of the compact object. A single gram of material, as it accelerates to near light speed in these jets, releases more energy than if it had undergone nuclear fusion. SS433 is a cosmic particle accelerator and a celestial lighthouse combined, proving that the most focused and efficient engines in the universe are not stars themselves, but the graves they leave behind, kept alive by a perpetual feast. The ultimate testament to stellar power is not always its ferocity, but its endurance across the eons. At the very edge of our observable universe, a solitary point of light defies both distance and time. Its name is Earendel, an ancient word meaning morning star, and it holds a record that redefines our cosmic perspective. This is not a galaxy, a cluster, or a nebula, but a single, identifiable star whose light began its journey to us when the universe was less than 1 billion years old. For nearly 13 billion years, that photon has traveled through the expanding void, a messenger from the cosmic dawn. Detecting such a faint, impossibly distant speck would normally be utterly impossible, even for our most powerful telescopes. Earendel's revelation required a perfect cosmic alignment, a natural magnifying glass of staggering scale. Between us and the star lies a massive cluster of galaxies whose combined gravity acts as a gravitational lens. This phenomenon, predicted by Einstein, warps the fabric of spacetime itself, bending and amplifying the light from objects far behind it. In this case, the cluster distorted space into a natural telescope, magnifying Earendel's faint glow by a factor of thousands and stretching it into a long, thin arc across the sky, a chance alignment that turned a theoretical possibility into a breathtaking observation. Analysis of its light suggests Earendel is a massive B-type star, likely many times hotter and more luminous than our Sun, with an estimated mass potentially hundreds of times greater. It is not a red giant or a hypergiant from a later cosmic era, but a brilliant blue pioneer from a time when the universe was young, metal-poor, and radically different. This is where Earendel's true power lies, not in its specific luminosity, but in its role as a time capsule. It allows us, for the first time, to study the detailed chemistry and physics of an individual star from the universe's first billion years. We are looking at one of the early architects of cosmic illumination, a star whose fierce radiation helped reionize the primordial fog of hydrogen that filled the young cosmos, making the universe transparent to light. Its violent life and eventual death would have seeded its surroundings with the first heavy elements, the foundational ingredients for everything that followed. The second generation of stars, the first planets, and the potential for life itself. Earendel represents the ultimate origin point for the very story we have been telling. It is a glimpse at the primordial engines whose power, repeated across the early cosmos, lit the darkness and began the long, intricate chain of creation that led to galaxies, to our Sun, and to us. From the primordial dawn of Earendel to the ticking bombs in our galactic backyard, we have witnessed the full spectrum of stellar power. We have met mass monsters like R13601, stars so heavy they strain the laws of physics. We have stared into the vast, tenuous atmospheres of size kings like VY Canis Majoris, where a single star could swallow our entire solar system. We have seen the unstable fury of luminous blue variables, the high-speed escapes of runaway cannons, and the exotic, terrifying remnants they leave behind, from magnetars with star-quaking magnetic fields to microquasars firing relativistic jets. This is not a catalogue of random anomalies, but a portrait of the universe's fundamental forges. Every atom in your body heavier than iron, the calcium in your bones, the oxygen you breathe, was forged in the heart of a massive star and scattered across the cosmos in its violent death. These titans are the ultimate recyclers. Their fierce radiation and stellar winds sculpt nebulae, triggering new star birth. Their supernova explosions enrich galactic gas clouds with the heavy elements necessary for rocky planets and the complex chemistry of life. Their very lives and deaths dictate the structure and evolution of galaxies themselves. So the next time you look up at the night sky, remember this. That serene tapestry of twinkling lights is an illusion. Behind each point is a story of unimaginable violence, of titanic forces, of life, death, and rebirth on a cosmic scale. You are literally made of stardust, the legacy of these celestial giants. To keep exploring the wonders and mysteries at the extremes of our universe, be sure to subscribe for more journeys to the cosmic edge.